In this video, we'll look at how to apply energy analysis to a problem in which work by non-conservative forces is present. This problem came about because one morning on the way in from work many years ago when I was teaching at West Point, I heard a news story about a lawsuit that was going on in which a person was suing because they had been hit by a large crate that had been slid down an incline and then across a tarmac at an airport and then banged into the person who wasn't expecting it. The argument for the people who were being sued was that the person couldn't be hurt because the particular package would have stopped before it hit them had the person obeyed the rules and been behind a particular line. And so I decided to create a problem off of it. A postal employee throws an 8-kilogram package off the airplane and onto the top of a 12-meter long frictionless ramp. The package is traveling at 7 meters a second at the top of the ramp. After sliding down the ramp, the package slides across a level runway with a 0.25 coefficient of kinetic friction until the package comes to rest. Alright, so that's basically what we have. 7 meters per second up here. So I'm going to put that. V initial is 7 meters per second. It's eventually going to end up over here somewhere. V final is going to be 0 because it's going to be at rest. I can set my y-axis 0 point anywhere. I'm going to set it here. And that means I'm going to set this thing to be my initial y. This ramp's length, which we'll call L, of course is related to y, so y final is 0 meters, L is 12 meters, mass is 8 kilograms, and mu is 0.25. And if we've done a good job, we know that, by the way, all the friction occurs here. There is no friction there. How much work was done by gravity on the package? Well, the work by gravity is equal to minus the change in potential energy of gravity, by definition of what a potential energy function is. So this would be minus U gravity final minus U gravity initial. But its final potential energy is 0 because it's at where I call the y equals 0 potential energy reference point. So this says it's equal to whatever the initial potential energy was. So the work by gravity is equal to mg y initial. Now I don't know y initial, but I know it in terms of L. Y initial, which is this distance. Oops. Let me get a different color I thought I had. Is that length. And that length there is related by the sine function. So this is mgl sine of 30 degrees, which is a half, which is mgl over 2. So the work by gravity is equal to 8 kilograms times 9.8 meters per second squared times 12 meters divided by 2. Well, 12 divided by 2 is 6. 6 times 8 is 48. 48 times 10 is about 480. Hopefully you've been practicing your mental math all semester. 470.4. Or about 470 joules. It's positive work. Of course it's positive work. That tells us that the gravity is trying to speed the block down. So as the block goes to the bottom, it's going to be going faster than it was initially. Let's do the next part. How much work was done by friction on the problem? Now here's an interesting thing. Most people think that they need to do some sort of force dotted into displacement. But the problem they have here is that you were not told how far the block would go. So you don't know the displacement of the force. So you cannot attack it from that approach. Here's an example of where the work energy theorem comes into play. So kind of a tricky part of the problem. W net is equal to the change in the kinetic energy of the block, which is in Kf minus Ki. Now you can choose to solve that at any point that you want over any part. Think of it as a motion picture. You can choose to stop the picture or start the picture anywhere you want. In my case, I'm going to start the picture here, and I'm going to stop the picture there. At the very end, it has no kinetic. At the very beginning, it had kinetic, 7 meters per second of velocity, and it had a particular mass. So that's what I'm going to use. During this period of time, there will be forces that are doing work on it. And during this time here, there will be my work by friction. So all of that's going to be on the left-hand side under the W net. So, like I said, there's no kinetic energy at the end. 1/2 mv initial squared with a negative sign is the total change or the total work that was done on it. Now what was work? The work was the work by friction, the work by the normal, the work by gravity, and that's it. It's the only three forces acting on the block during the problem. And this is equal to minus 1/2 the mass times the initial velocity squared. That's the initial kinetic energy. But the normal force does no work in this problem. How do I know that? Let me go back and look at my diagram. Here's the displacement vector going down the incline, but the work is perpendicular. The normal is perpendicular to it. So the angle between those two is 90 degrees. I might put that in there for you. So there's a delta R. And there's the normal. They're at right angles. And when force is perpendicular to the displacement, it doesn't change the speed of the object. It does no work. Down here at the bottom, the displacement of the block is in this direction. But down here, the normal force is perpendicular to it. So it does no work here. It doesn't speed up or slow down. I like to joke sometime and say, how much work could a normal force do if a normal force could do work? None. It's kind of that woodchuck thing that they used to teach us when we were kids many, many years ago, or at least when I was a kid. It's not true that the normal force can't do work. In an elevator, for instance, going up and down, the normal force, in fact, can do work. But for these type of inclined plane problems and sliding along a table, the normal force is perpendicular and it does not speed up or slow down blocks. If it did, this block could just take off on its own, and it doesn't do that. And it wouldn't take off down the inclined plane at all if it wasn't for gravity. It just sat there. So anyway, the work by the normal force is nothing. That's zero. Sometimes they ask you that. That leaves only two things: the work by my friction force, which is what I want to find, and the work by gravity. So Wf is minus 1/2 mv squared minus Wg. So that'd be minus 1/2 times whatever the mass was. I have to go back up and look up my problem again. My mass was 8 kilograms and my speed was 7 meters per second. 8 kilograms, 7 meters per second squared minus 470 joules. And if you put all that in, you're going to get a kind of an interesting number, minus 666 joules. In the Bible, of course, 666 is the mark of the beast, the Antichrist, or evil. So, as you probably guessed already, physics problems can be evil. All right, so kind of just purely by chance and luck that number came out, but that's what came out of the problem. So the total work by friction minus 66 joules. There's more negative work by friction than positive work by gravity. So the net work is negative, the block slows down. And that's what we know. It was going 7 meters per second at the end, it's rest. The last part of the problem asks you how far along the runway did the package slide. So let's see if we have enough time to finish this one. We have a block here, and we have friction going this way, and we have a normal, we have weight, and we have a displacement, delta R. Now the sum of the forces in y is equal to MAY. There's no acceleration in y. So the normal minus the weight is 0, or the normal is equal to mg. The friction force is equal to mu times the normal, or mu mg. This is all from the previous discussion about Newton's laws. The work by friction has to be equal to the friction force dotted into the displacement. In our case, this is going to be equal to mu mg, the distance that the object travels along the tarmac, and the cosine of 180 degrees. Let me show you that back on the main diagram. So what I'm talking about is this distance that it travels. That's d. And the displacement vector, which is in this direction, and the friction vector, which is in the opposite direction. So there's 180 degrees between those two arrows. And now I'm rushing a little bit, but trying to finish the video in the time frame. So this cosine of 180 is minus 1. So the work by friction is equal to minus mu mgd. So d is minus the work by friction divided by mu mg. Well, that's minus a minus 666 joules divided by, I believe we had an 8 kilogram block, and we had 0.25 for the coefficient of friction. 0.25, 8 kilograms, 9.8 meters per second squared. So 666 divided by 9.8 divided by 0.25 divided by 8, 33.979. The distance is 34 meters. So if the person had been, say, 50 meters back, the block would have fully come to rest well before it ever struck them. So the secret was to make sure they were far enough back that this package couldn't hit them. Now what engineers will do is they know that this may vary and this package may have a slightly different mass, which will change the energy but also changes the friction force. They simply make it so that the person has a line with a safety margin such that there's no way the package could have enough speed and energy to reach where the person is. And they like the person close so that they can reach across the line, grab the stationary package, and take it off. And so you can just throw them out of here, they slide down, and in fact you could control the coefficient of friction by changing what you put as a material here on this runway. It could be some sort of a plastic, it could be some sort of a rubber. Anyway, that's how real world problems, physics problems, become real world problems. And you start, if you do that for a job, regardless of your degree, as physics major, whatever, then they would call you an engineer because you're applying it to a particular problem. If you're developing the laws of physics to understand the entire thing, and you're looking at a much deeper type thing than just a particular problem, then they would call it research. You'd be called a physicist.